Hi, I'm going to go over the test and basically give you the solutions. Without going into too much details, you can fill in the missing steps. But let's start with number one. Number one was asking to look at this circuit here and to identify resistors that are in series or in parallel. If we start with series combinations, well, to have two resistors in series, they must be in the same branch. And another way of saying that is that they should not be separated by junctions. Or you should be able to go from one end of one of the resistors to one end of the other one without going through a junction. And it's pretty clear here that you cannot do that for any of the resistors here, but you can do it for R1 and R2. You can go from this end here to this end here without going through a junction. Or another way of saying it is that R1 and R2 are in the same branch. Okay, so that's it for the resistors in series. Those are the only two that are in series. In parallel, you must be able to draw a closed loop that contains only two resistors, not three, but two at a time. And one such closed loop is this one here. If you go along this closed loop here, then those two resistors are the only elements, circuit elements along the loop. So those two are in parallel. It turns out that those are not the only one that are in parallel. You can also do another loop. So that's one. So R4, R6 are in parallel. Another loop you can do is the following that contains only two resistors is this loop here. If you go like this here, go down like this here, and then up, then and you go back, the only two resistors along that loop are R3 and R7. So those two are also in parallel with one another. So there were two pairs of resistors in parallel, R4 and R6 together, and R3 and R7. So that's the first problem. The second question, well, uh, it was the one where you had to calculate. Well, let's go. Let me show you the actual question. So number two, you had the wire made of a metal with a density. This is the density, the mass per volume given by this value, a resistivity given by this, and a molar mass of 75 grams per mole. And you were told that each atom provides two free electrons. You have the length of the wire, you know the voltage applied to it, and you know the current that flows through it. First question was to find the radius of the wire. So how do we do that? Okay, so look at the information we have. So we're looking for the radius. Obviously, we'll have to find the area, the cross-sectional area first. So how would we do that? Well, okay. So some people start with this equation. Volume is equal to L times A. So this is A is the cross-sectional area. So you say that's what we're looking for. Once you have A, you can find the radius because A is equal to pi r squared. We know the length. This is 80 centimeters or 0.8 meters. So it looks like maybe we could try to use this equation, but we don't know the volume. So actually, this is a dead end. You cannot use that equation to solve the problem. Uh, no, the volume here would be what? Is the length of the wire times the cross-sectional area of the wire. This volume here is the volume of the wire. We have no information about this. A lot of people calculated the volume here, and what they did was to calculate the volume of 1 mole of that material. But the volume of 1 mole has nothing to do with L times A. L times A is the volume of the wire, and that volume we don't know. You cannot set this volume equal to the volume occupied by 1 mole. Those are totally different volumes. They have nothing to do with one another. This is like saying that the wire that we have, which is 80 centimeters long, necessarily contains 1 mole of that material, and that we don't know. So there's no way to use this equation here to find the area. What you have to use is you have to go through this equation to find the area, the resistance in ohms, is equal to the resistivity, this is the resistivity, times the length over the cross-sectional area. That's the way to find the area and then to find the radius. So how do we find that? Well, first of all, we had to find the resistance, but we have the voltage and the current. So you do voltage over the current, you find this. This is the resistance of that wire. Now we have the resistance, we can go back and find the cross-sectional area. From this equation here, the area is rho L over R. Again, this rho here is not the density, it's the resistivity times the length of the wire divided by the resistance. Resistivity was this value here in ohms times meters multiplied by the length, which is 0.8 meters, divided by the resistance we just found, and that's it. That's the cross-sectional area in meters squared. Once you have that, you set that equal to pi r squared and you solve for r. R is just, because the area is pi r squared, r is the square root of a over pi, and this was the answer. 1.07 times 10 minus 3 meters, or if you want 1.07 millimeter. That's the radius. Okay, part two. Well, part two, again, let me show you the question sheet. Okay, part two was to find the drift velocity of the free charges. Okay, so the drift velocity, well, it just appears in one equation, so that's pretty simple. First, to find the drift velocity, well, we have to find the density. Well, we have to first use the density, but the density you have to be careful because it was given in grams per meter cube. Sorry, grams per centimeter cube. So if you want to convert that to grams per meter cube, you have to use the fact that 1 centimeter cube is equal to this is 1 centimeter here, 0.01 meters. All that is cubed. The whole centimeter is cubed here, so you have 0.01 cube. So you have 1.25 divided by 0.01 cube, and you get 1.25 times 10 to the 6 grams per meter cube. Okay, it's positive 6 here because you divide by 10 to the minus 6, so it becomes times 10 to the 6. That's the density in grams per meter cube. I could convert to kilograms per meter cube. I don't have to here. If I converted that to kilograms per meter cube, I would have 1.25 times 10 to the 3 kilograms per meter cube. Okay, so that's the density. Now we can calculate the number of atoms per meter cube. This was the only, well, this step here, this is the only tricky part of the calculation. So now that was important to get that right because that's the only tricky point. Then number of atoms per meter cube is just given by Avogadro's numbers times the density. That's not the resistivity now, it's the density, rho, that we just wrote here, divided by the molar mass. So Avogadro's number here, atoms per mole, multiplied by the density that I converted to gram per meter cube, divided by the molar mass in grams per mole. Notice I left everything in grams here, so the gram here cancels out with this gram here. I could have converted to kilograms. I would change, here I'd have 10 to the 3 here, and this I would have to write that as 75 times 10 to the minus 3 kilogram. But in the end, the ratio gives the same thing. You get this here. Okay, so I didn't really need to convert to kilograms because anyway, the grams cancel out. This is this number here is the number of atoms per meter cube. Okay, and in the formula sheet that was written exactly this way. You have the full equation with this quantity here written in words to make it really clear what this is. Now we need the number of free electrons per meter cube, and here because each atom was providing 2 free electrons, the number of free electrons per meter cube was just this number here multiplied by 2. So the number of free electrons per meter cube is just twice that. So it's 2.008 times 10 to the 28. I didn't write it here. It would be 3 electrons per meter cube if I wanted to write that. But the real unit is just per meter cube. So that's the number of free electrons per meter cube. And then I go back to this equation here. And so this drift speed, which is what we're looking for, is the current divided by the number of free electrons per meter cube that we just calculated times the charge of 1 electron times the cross-sectional area of our wire. So this is the number of free electrons per meter cube, multiplied by E, the elementary charge, multiplied by the area that we found earlier. And you plug everything together and you get this here for the drift speed. 1.71 times 10 minus 3 meters per second, or if you want, 1.71 millimeter per second. Okay, which makes sense. We know that the drift speed is very, very small, of order of a few millimeters per second usually, so that's what we get here. Okay. Now problem 3. Well, problem 3 was simply applying Kirchhoff laws. So I won't get into it straightforward. There was no trap here. Here we have 3 branches, one here, a second branch here, and a third branch here. So there were 3 currents. And you just set up your 3 currents, you apply the rules, the algorithm I gave you, you set up the currents, you assign polarities, you do loop rules. And here it was very simple because there's no resistor in this branch here. So when you do the loop rule here, you can actually get the current flowing here in one step. You don't have to do algebra. You just, well, there's almost no algebra to be done, and you get directly the current here. If you do the loop rule here, you get the current flowing here in one step. And once you have the current here and the current here, you can find the current here by applying the junction rule here. So anyway, the final answer is that first you get the current flowing here, and it turns out that the correct direction is to the left here. The current here is going this way, and the current here is going this way. And the values here are this current here. The top one is half 1 amp. So this turns out to be 0.500 amps. This is the current in the top branch flowing this way. The current flowing here comes out to be 0.100 amps, and the current flowing here is 0.600 amp. Okay, so those are the correct directions. And if you want to see the actual values, they're here. They're given here. So that's the current flowing at the top to the left, 0.5 amps. This is the current flowing down along the diagonal, 0.1 amp. And this is the current flowing up in the right branch, 0.6 amp. Okay, that was problem 3. Now problem number 4, let me go back to the, so the formula sheet is here, but it refers to, let me go back to, actually to this. Okay, so number 4 was here. Number 4, you had to find, well, there were 2 questions. First was to find the difference of potential between point A and point B. I told you there was a short way to do it. You could, if you want, you could solve and find the currents everywhere. But here, if I go from A to B, I can avoid all resistors by going this way. So if I go this way, now as I go here, I drop, the potential decreases by a value equal to 9 volts. So here, as I go this way, I get minus 9 volts. And then what I can do here is that I can avoid all resistors by going like this here, and then going like this, and ending up at point B. Okay, so I'm going this way. I'm going from point A to point B. Here I drop by 9 volts. So I have minus 9 volts of voltage. And here I increase by 12 volts. So as I go from A to B, I get minus 9 plus 12. So as I go from A to B, I get a total change of potential of plus 3 volts. That means that as I went from A to B, here I went down by 9 volts, and then here I went up by 12 volts. So the net change is plus 3 volts. That shows us that as you go from A to B, you end up increasing your potential. That means that point B is 3 volts above the potential of point A. So in absolute value, the difference of potential between A and B is 3 volts in absolute value, with point B being at a higher potential than point A by 3 volts. Okay, so that's the way you find the difference of potential without solving the entire circuit. Finally, The other question, the bonus question, or you can use one or the other as a bonus, was to find the current in R1. But the key point here is that R1 here is, you see here, is in parallel with an ideal wire here. So there's a short circuit here. R1 is short circuited. That means that there's actually no current flowing through R1. There's no current in R1. And that was the answer. There's no current flowing through R1 because it is short circuited. There's a short circuit with R1 and an ideal wire here. Of course, you can just apply the loop rules and find the currents everywhere. That would be very long. That's very long, but you can actually prove it. It's not that long. You can prove that there's no current here if you use a Kirchhoff laws. Okay, and that was it. That was the test. Thank you.